Okay, if not, I'd like to talk about a completely unrelated subject, spreading resistance profiling. You may never heard of this before. This is SRPs for short. And this is a technique used to analyze resistivity versus depth in an integrated circuit. And this is accomplished by taking a piece of a wafer and carefully grinding it with a shallow bevel, as shown here. And then you take a set of these probes and you very carefully move them down the bevel, measuring resistance as you go. This technique gives you resistivity versus depth, but it can also detect whether a material is N-doped or P-doped. And I think they do that by heating one of the probes. I'm not 100% sure exactly how they detect P versus N, but I know it has to do with heating one of the probes. By taking these measurements and carefully calibrating it, it can give you a junction depth and doping profiles, which are very useful when analyzing a process. And I'm going to show an example of what that looks like in a minute. Silicon Labs in Reno, Nevada is the leading vendor for generating SRP data. We don't do this here. If we need SRP data, we send it out to Reno to have them do it for us. And here's an example of what their probe setup looks like. You can see there's a little sample down here. It's been beveled at a very shallow taper. You can see the two probes here, and these manipulators are going to very carefully move down, taking resistance measurements as they go down the shallow bevel here. And this is what they give you, a plot similar to this. This is an example of what an SRP might look like. SRP stands for spreading resistance profile of an NPN bipolar transistor. Show a cross-section of a bipolar transistor. This SRP is right where I've drawn this yellow line here. So it's right down through the emitter, base, collector, buried layer. And so what this is showing you is concentration on the y-axis and depth in microns on the x-axis. Here you can look at the N plus emitter. It's way up here, somewhere around 10 to the 20th carriers per cubic centimeter. Then as we move down into the P base region, it's somewhere in the 10 to the 17, 10 to the 18 carriers per cubic centimeter. And with a junction depth of maybe 0.2 microns. And then the P base to collector, the collector's down here, maybe 10 to the 15, 10 to the 16 carriers per cubic centimeter. This gives you an idea how narrow the base region is. You need a very narrow base region to get a decent beta on a bipolar transistor. The reason there's two plots here is because of the difference in depth. This is very shallow, so they did a very shallow bevel to get all this data. And then they wanted to get the buried layer in here, but it was much deeper. You can see it's down in these 5-6 micron range. So they did a much steeper bevel so they could measure this, but it's all still measuring on this yellow line here. And you can see you pick up right here with the NFE collector, and now the buried layer concentration goes up, and you can see it's peaking somewhere around 2 microns deep, but the buried layer is spread out because it's been in there a long time. It's had a lot of time and temperature to move during the process cycling. It's one of the very first layers you put in. Again, I just wanted to show what spreading resistance profiling looks like. Now, Richard tells me there's a much newer way to do this. And what's it called, Richard? SIMS? S-I-M-S? It uses an ion beam to etch into the wafer through, I want to say OJ analysis, what type of material it is. So it gives you a very similar curve to what we're showing here, where you get a profile showing concentration, and whether it's P or N material, and depth as it etches down through the part. SRPs have been around since the 1970s. This is probably, I don't know, maybe 90s technology, some 2000, probably way more modern. But I just wanted to if you hear people talk about SRPs, this is what they're talking about.